Welcome back. Today we're going to finish up Chapter 1. See, it says Chapter 1. Today we're focusing on process management, memory management, storage management, and computing environments. Here are the chapter objectives one more time. Remember, a process is a running program, hence a program is passive, the process is active. In order to run, remember from CS220, a running program, a process, needs CPU cycles and memory. In the real world, a process also needs access to I/O devices, and files are an abstraction of I/O. So when the process starts up, the operating system has to provide these resources, and when the process terminates, the operating system has to clean up after the process and reclaim those reusable resources. Of course, you can't get CPU cycles back. We remember from CS220 the concept of a program counter, and there's one program counter per process. If you're running a multi-threaded process, there's one program counter per thread. Also a difference from CS220, where we just thought about one process running. Typically in a real system, there are multiple processes running, and they're all competing for these limited resources. These are the typical operations that are performed on processes. There's not a whole lot to say here. We'll be seeing later on mechanisms for process synchronization and communication, and we'll be looking at deadlock handling in a general sort of way. Memory management is the mechanism by which the operating system decides how much memory, and here we mean RAM, to allocate to each process, and manage the transfer of data between memory and disk. Disk, when we're talking about virtual memory, is used as backing store to RAM. So just as we saw in CS220 with the transfer of data between registers and memory, memory management will transfer blocks of data between memory and disk. If too little memory is allocated to each process, then the operating system will be spending a lot of time doing transfers between memory and disk. That's overhead. That's something called thrashing. It's not useful. If the system gets into a thrashing state, then the operating system will have to prioritize the processes and suspend some, reallocating their memory to other processes in order to get out of the thrashing state. Storage management is the management of blocks of data on I/O devices such as disk drives, flash drives, any sort of storage device. The operating system has to keep track of which blocks are in use and which ones are free. Then layered on top of that management layer is the file system. A file is an abstraction of storage. We consider it to be a stream of bytes, and the operating system will always allow us mechanisms to group files together, i.e. directories and folders, and give us ways of creating files, deleting files, reading files, writing files, those typical sort of management operations. All right, I don't see anything to really comment upon here. Here we can see some attributes of the various layers of the memory hierarchy. In particular, look at the access time of registers, a fraction of a nanosecond. Main memory access times are much greater than that, hence the use of caches to try to make main memory appear to be faster to the CPU, and then compare access times of main memory to magnetic disk, and then think about how efficient virtual memory has to be, since we're trying to provide a memory space that has the speed of main memory, but the storage capacity of the magnetic disk. We can't be going to disk too many times when we're using virtual memory. I don't see anything to comment upon here. One of the things the I/O subsystem does, as you can see here, is provide abstractions of all the types of I/O devices that we have on a system. If I want to print, I don't want to be thinking about if I have a PostScript printer or an HPCL printer. Similarly, if I want to read data from a file, I don't want to have to think about whether I'm reading from a SCSI disk, an SATA disk, an IDE disk, a flash drive, what have you. So we work with abstractions of the devices, and the I/O subsystem, through device drivers and through its own design, take care of all the details for us. When I was your age, and yes, we did have computers back then, I used a mainframe computer that was far, far away, buried in the computing center, and what I interacted with was what was known as a dumb terminal. Then in the early 80s, the PC came around, and the computing power got distributed to users' desks. Today, to some degree, we're seeing the transition back to that centralized computing center with cloud services and things like thin clients, which we have in some of the computing labs today at Goucher. No comment here other than, boy, things can change quickly. Once upon a time, BlackBerry was the leader. All right, in this course, we'll be vaguely aware that there are these things called networks, but really this is getting into the topics of a networking course, so we won't be spending too much time on these sorts of things. All right, more topics for a networking course. More networking. Virtualization is an interesting, relatively new area in operating systems. So as we said last time, an operating system abstracts the hardware for user programs. Virtualization abstracts the hardware to a degree that multiple operating systems can be running simultaneously on the same hardware. So that's a different sort of an abstraction than we see from a traditional operating system, with the abstraction that it provides to user programs. A couple of the great things about virtual machines are, and we'll see them in this course, it's pretty cheap to lose a virtual system. So when you're working on your kernel projects, if you wipe out the entire file system, all I have to do is copy the virtual machine files back for you, and you're back up and running. Another advantage is I can give you root access on the virtual machines. I wouldn't be so comfortable giving you root access to Phoenix. Here you can see a traditional operating system on the left and one architecture for virtualization. Interestingly, VMware uses a different architecture. VMware's software runs on top of a host operating system, and then the guest operating systems, and in this case, think of these as the guests, run on top of the VMware software. I'm forgetting at the moment the name of a virtual machine manager that runs on top of their hardware. All right, so I just looked it up. Xen, X-E-N, is an example of a VMM that runs on what's called the bare metal, the actual hardware. It's interesting to think about the difference between client server computing and cloud computing. One definition I ran across was if your server is on within your organization's network, it's client server. If it's outside your organization's network, it's cloud computing. So for example, if you're using Phoenix, you're doing client server computing. If you're using GouchoLearn, and GouchoLearn's server is off-site, then you're using cloud computing. Here's a diagram illustrating that. The Space Shuttle was a great example of an embedded system with a real-time operating system. The Space Shuttle was aerodynamically unstable. The only thing that allowed it to glide were the control computers updating the flight surfaces approximately 25 times a second. And if the operating system got behind on those updates, well, it would fall like a rock. Fortunately, that never happened. Open source software gives you the power to make whatever modifications that you want. Linux, the operating system, is open source. GNU is the set of application programs that run on top of Linux. There's the BSD family, FreeBSD, OpenBSD. Linux is so popular we don't hear so much about the BSD variants anymore. I think Android is open source, but working with it, I'm not sure is as easy as working with Linux. OS X is closed source. I'm pretty sure you can't simply pick up source code for OS X. Windows, Microsoft Windows is closed source. All right, so that finishes chapter 1. Any questions? Why don't you guys ever have any questions?